You might know how to solve linear systems, but the shape of their solution sets is often overlooked. A system of linear equations can only ever have 0, 1, or infinitely many solutions, never exactly 2 or 3. That might seem unintuitive at first, but once we look at the geometry behind linear equations, the reason becomes clear. Hey everyone, welcome back. If you're new to this channel, I'm Oliver, a computer science student and tutor. On this channel, I focus on short, intuitive explanations of core maths and computer science concepts. Today we'll explore the solution spaces of linear systems and see how geometry explains why systems have no solution, a unique solution, or infinitely many solutions. So here we have our linear system of equations, and what we care about is this x, and specifically which x's satisfy this equation that make this matrix vector product equal to this vector on the right side. As I have already mentioned, such a system has only 3 possibilities for its solution space. Either there is no solution, so no x satisfies the equation, there is exactly one solution, so the x is unique, or there are infinitely many solutions, so the set of x's that satisfies the condition is infinite. It is not possible for such a system of linear equations to have a finite number of solutions that is not 0 and not 1. This means that our equation a times x equals b cannot have 2 solutions, cannot have 3 solutions, it can't even have 10 million solutions. It either has 0, 1, or infinitely many. In short, the intuition behind this is that linear equations represent flat objects, such as lines and planes, and these cannot intersect in finitely many scattered points. They always intersect either in no point, exactly one point, or infinitely many points. To understand why these are the only possibilities, it helps to look at the geometry. First, we'll take a quick glance at this linear system of equations. It's a 2x2 linear system of equations. So there are 2 unknowns and 2 equations. The 2 equations being these down here. So what this matrix vector multiplication being equal to a vector means is equivalent to what these 2 equations mean. If we resolve this left matrix vector product, we get exactly these entries. Then these linear equations can be rearranged. So we write one entry in terms of the other entries. And we see now that these just represent lines. So we have a y-intersect here, and then our gradient. So by how much our line goes up for every step it goes to the right. I have sketched these lines into this graph. So the green line representing the first equation and the orange line representing the second equation. This is one way of representing these linear equations. And then the solution space of them is exactly their intersect. So in this case, you can see the orange and the green line only intersect in this point here. And that then represents our solution for this linear equation. Now let us look at the other 2 cases. In this case, I am not using a matrix and just showing the lines, so the intuition becomes clear. In this case, both our lines run parallel to each other, so their gradient is the same. However, their y-intercept is different. In this case, our lines never intersect. This means that our linear system of equation has no solutions. Now, the last case is when there are infinitely many solutions, and this happens when we have the same line. So if we increase our y-intersect of this line until it reaches the y-intersect of the other line, both of them having the same gradient, we will have infinitely many solutions. Regardless which x1 we look at, both of these lines have the same x2 value. So there are infinitely many intersects between these lines. I want to also show what this looks like in 3D. Now, 3D is a bit harder to draw, so I will use this online representation. In 3 dimensions, we have 3 variables, x, y, and z. This means we have three coefficients, a, b, and c. Because we have three variables, a single equation no longer represents just a line, but it now represents a 2D plane. This you can see in black, brown, and blue. So each of these planes represents one of these equations. You can see in this case, these three planes cut in exactly one point, which is this white circle or sphere that is currently rotating at the bottom. Now we can also have the case in which two or more planes are parallel. So in this case, two of the three planes are parallel. Because they are parallel, none of their points intersect. And for this reason, with or without this third orange plane, we would have no solution at all. So no point that lies within all three of these planes, or even just the two planes, plane 2 and plane 3. Now, in our case, for an infinite number of solutions, there are several cases for which this can be true. One such case is when several of our planes cut and have an intersect of a line. This would be equivalent to the case where we have in the two-dimensional space two lines which are the same, so they have an infinite number of points in which they intersect. With our planes, these do not have to be the same planes in order for them to intersect in an infinite amount of points. They can be different, they just need to align in a certain way, like in this case. The same is the case if we just have two times the same plane. So in this case where we have three planes and two of them are equal. So we have two planes which are not parallel, so they cut or intersect in a line. Now the last possibility we have is that all of our planes are the same plane. So in this case, it's similar to when we had two lines that were equal, so there is still an infinite number of solutions, but now our solution set is no longer represented only by a line, but by a plane, meaning that while a line represents an infinite number of solutions, a plane you could think of as representing a two-dimensional infinity of solutions. Now this becomes a bit more complicated, but the idea is that our solution space is represented by a vector space. So it by itself has directions, and it can have a certain number of directions. This means that while the number of solution remains infinite, the way our solution space looks may vary. Now let's take a brief look at how we identify the number of solutions from a system's matrix form. So this is how you could tell in practice how many solutions a linear system of equations has. In this case, we have our linear system of equations represented in this form, where our system matrix, so A, is on the left-hand side, and our B matrix is on the right-hand side, separated by this vertical line. This is sufficient for defining a linear system of equations simply because our number of variables is defined by the number of columns, and since they're variables, this is what we're trying to find, and we have no further information on it. Now, a linear system has a solution exactly when row reduction does not produce a contradiction. So row reduction is a process which turns our extended matrix, so with B on the right-hand side and A on the left-hand side, into this row-echelon form, where we have a type of staircase form in each of these cases. Now I've noted here that these green stars are non-zeros. This is what our row-echelon form is defined by, so this is a step where we have non-zeros. Because we have a zero here, this does not count as a step. And this regular star is for any value, so it can be 0, it can be any other 0. Now, a quick note, more formally, this can be defined using the rank. So this number of steps is just an informal way of saying it's the rank of a matrix. But for brevity, we will not discuss this here, as I've also made a video on this, which you can take a look at. Now, these three cases are just exemplary cases for 3x3 systems, but they represent telltale signs for when a system has no solution, one solution, or infinitely many solutions. So in our row-echelon form, when you see that there's a 0 row on the left-hand side, so left of the vertical line, but there is a non-zero entry on the right-hand side, this is a contradiction. If we check the matrix vector multiplication from our equation AX equals B, it means this 0 row multiplied by our variables, but since this is a 0 row, multiplying it gives us just 0. So this left-hand side is just 0, being equal to a non-zero number. So that's what our last equation says. It says 0 is equal to not 0. And that is exactly the contradiction, which causes this equation to have no solution. Now, in the second case, when we have no 0 rows, and this would be for a square matrix, so where the number of rows and columns is the same, we have exactly one solution. Meaning that if you see a square matrix where the row-echelon form goes through the entire matrix, meaning there's no 0 rows, regardless what our vector B is, there is always exactly one solution. And the last case is that there are an infinite number of solutions. And for a square matrix, this is when we do have this 0 row, which before caused us a contradiction because we had a non-zero value here, but now there is a 0 value here. So this last line just says 0 is equal to 0, but that is always true. So only these two equations are relevant. Now you can use this as a cheat sheet for square matrices, but these are already row-reduced for simplicity. Matrices, in the wild so to say, do not always have this row-reduced form. And for that reason, it's valuable to know how to modify a matrix in order to reach this row-reduced form. If you'd like to see how these patterns actually arise in practice, check out my video on Gaussian elimination, where we compute row-echelon forms step by step. If you want to continue from here, you'll also find a full linear algebra basics playlist on the channel. Subscribe to stay up to date with new videos, and as always, thanks for watching.